All right, in this video, we're really moving into the physiology of bone, right? How it develops, how we use it to grow, and then also this lifelong process called remodeling. So as far as bone development goes, there's really two main ways this happens. We have what's called endochondral ossification. So ossification is what you should think of with development. Ossify is like harden, osseous tissue, bone, right? So this process of becoming bone, developing into bone. We have two different ways this happens. We have endochondral. Did not leave myself enough room. Endo within, chondro, that prefix means cartilage. So we're going to see a lot of our bones actually starting out as this hyaline cartilage template and then becoming bone. There is also intramembranous ossification. And that's going to be more in the flat bones. They actually start out in this fibrous connective tissue and develop from there. But notice both of these forms of ossification are going to require some kind of precursor connective tissue that then is going to turn into bone. So let's look at those processes. Then we'll talk a little bit about how bones grow. They grow, let's just put this out here first. They grow both in length, we call that interstitial growth. And there's a whole process with those growth plates for how that happens. And then there's also appositional growth, which is actually an increase in diameter. The bone's getting like thicker or more robust. And then at the very end, we'll get to this idea of remodeling, which again is a lifelong process. Okay, so as far as development goes, we have endochondral ossification and intramembranous ossification. Look at that, I had it all written out for you, right? Endochondral, again, this is that hyaline cartilage template. This is going to be the majority of our bones, long bones, short bones, that sort of thing. Intramembranous, particularly here we think of the flat bones. A fibrous connective tissue is the template there. So you have a couple amazing images in your textbook that kind of lay out this entire process. Endochondral ossification starts out with this hyaline cartilage template. Okay, and what's going to happen here is some of the chondrocytes in the center of this little precursor bone, this little chunk of cartilage, some of those hyaline cartilage cells, the chondrocytes, are actually going to die. They're not getting the nutrients they need, and as they disintegrate, they kind of leave these hollow, empty areas in the center of this developing long bone. The next step, what we're going to see happen is blood vessels actually kind of moving up adjacent to this hyaline cartilage template. You see kind of more and more space opening up in the center here. But this blood vessel brings with it these fibroblasts, right? Different connective tissue cells. These fibroblasts are actually going to convert into osteoblasts. Remember, fibroblasts are just making collagen. Osteoblasts have to make these collagen fibers and then encourage calcium and phosphate to precipitate. So don't get too weirded out by them saying fibroblasts convert into osteoblasts, right? But notice that comes with this blood supply. And so what happens is we start to develop what they're calling this bony collar. And right, this is in cross section, but picture the entire diaphysis kind of getting this ring of bone on the outside. Okay, those blood vessels are then going to manage to actually penetrate into the center of this hyaline cartilage, and they kind of start taking up that space that was left by those dead chondrocytes. Again, with the blood supply, we bring these cells, and so we have more osteoblasts moving in and building bone. We call this the primary ossification center, right? The first ossification center. And so we see that kind of bone starting to grow along the center of this cartilage model. In our next step, we get some remodeling. Now, remodeling basically refers to the removal of bone from one area and the deposition in another. And so here we see kind of the hollowing out, the removal of that bone from the center. This is going to develop into our medullary cavity, but we'll also see a thickening of the bone along this diaphysis, right? And we see that kind of spreading throughout the diaphysis of this long bone, okay? Not a whole lot really of cartilage left there, except we see it at the epiphyses. So this bone is not done developing yet. We need to do this again in what we call the secondary ossification centers. So in this fifth step here, we see blood vessels entering both epiphyses, right? And repeating the same thing, bringing those osteoblasts, the formation of bone. In this case, we're gonna keep spongy bone in these epiphyses, and we see still the remaining cartilage in that epiphyseal plate or epiphyseal cartilage, and also the hyaline cartilage that stays on the articular surface even into adulthood, right? So this is kind of our bone development. Now, the hard part is now we sneak in a little bit of bone growth, because bone growth is really what takes place at that epiphyseal line, the cartilage that remains there. I'll keep it separate, we'll talk about it in a minute, but they're showing you here then in adulthood that cartilage is actually replaced by bone as well. So we'll come back to that thought, but this is endochondral ossification, right? Starting with this hyaline cartilage template, bringing blood supply in, and setting up both the diaphysis and the epiphyses as bone. Okay, we'll come back to interstitial growth. What I do want to make, oh my goodness, I wanted to mention before we go there, this other type of development, which here they're showing this taking place in the skull and the clavicle, that some of your bones develop differently in what's called intramembranous ossification, okay? It's very similar in the idea that you have a connective tissue, like a cartilage connective tissue precursor, and then the osteoblasts are going to come in and turn it into bone. So in intramembranous ossification, right, if you want to form, say, the bones of the skull, you have these mesenchymal cells. This is just like a very early connective tissue. Remember, those were all mesoderm in origin. That's kind of that same prefix here, right? And what we're going to see is that osteoblasts move into this tissue and start creating the matrix that we would actually recognize as bone. Things kind of pick up then as blood vessels start coming in here. There we go. So this blood vessel actually kind of gets surrounded and trapped in the matrix, and this is really going to pick up the pace of osteoblasts coming in, changing that connective tissue into another connective tissue, which is bone. Okay, more and more bone, and then what we're going to need, right, we're getting this spongy bone, blood vessels kind of all throughout it, but what we still need is that compact bone on either side. And so we get more remodeling, taking the bone that we have and adjusting it. But it's really cool, you can see, particularly in these flat bones, what a big impact the blood vessels actually have on how nutrients are delivered, osteoblasts are delivered, and then how that bone is developed. But the end result of that remodeling, we get compact bone on either side, and we keep that spongy bone down the middle, right? So that is intramembranous ossification. Okay, so then let's make sure we talk a little bit about growth. Interstitial versus appositional. So interstitial growth is making the bones longer, and this is occurring at those epiphyseal lines, at the cartilage that remained once that endochondral ossification was basically done, right? So this epiphyseal cartilage. So this picture is super cool. They're actually showing you the growth plates, right? And then as an adult, you don't get that kind of gap separating the epiphysis and the diaphysis, which is kind of cool. This picture is a little harder to follow, but notice where they are, right? They're basically looking at a portion that is bone already, and then our epiphyseal plate. So notice what happens here. In that hyaline cartilage, in that epiphyseal plate, basically what we're doing is we're going to keep pushing the new developing cartilage towards the end, right? And if we do that on both ends of a bone, it's getting longer, right? So notice this zone, they're calling this cell proliferation. Here the chondrocytes are actually multiplying, right, and pushing that cartilage plate further and further. But what's chasing them basically is ossification. So some of our cells are going to basically stop dividing, and chondrocytes get enlarged and are going to be replaced by bone. So this zone here, they're calling the zone of calcification, right, where the matrix is starting to build. This bone deposition shows really a lot of remodeling. They're saying part of it is being broken down, and instead of chondrocytes, now we're going to get osteoblasts. With osteoblasts in the location, this is bone. So without getting too crazy, you do not need to memorize what these different zones are, but I want you to realize is that cartilage is still dividing, and so as we're adding cartilage, the bone is getting longer, and kind of those cells that aren't getting pushed towards the end are slowly getting ossified, right? The cartilage is being replaced by bone. That is what we mean when we talk about interstitial growth, right? That's making long bones longer. Appositional growth is making them wider, right? And so what's happening here is that on the outside, remember that outer covering is called the periosteum. There are osteoblasts there that are adding to the outside of the bone. Around the medullary cavity, right, we had an endosteum, that's the covering of the medullary cavity from the inside, and there we have osteoclasts actually pulling that bone apart, right? So we can, the compact bone, that ring, right, on the diaphysis doesn't need to get thicker, but we can make the whole bone thicker and kind of hollow out the inside. And so that is appositional growth when those bones get wider and thicker. Okay, so see how those two kind of got squished together, but we already went through intramembranous ossification. Okay, this bone remodeling is the part that happens throughout your life, right? And so I picked up this little scales of justice here. What we're looking at are how osteoclasts and osteoblasts both do their job, and if we do this in a balanced fashion, we get this very appropriate bone remodeling. We'll look at some different factors that might adjust that and might create an imbalance, right? If osteoclasts are doing too much work and osteoblasts can't replace it, you might be worried about things like osteoporosis, right, as we start wearing that bone down. But bone remodeling is really important in allowing bone to adapt itself to stress throughout your lifetime, right? This idea, and I don't think I mentioned it earlier, this is actually called Wolff's Law, this idea that bone lies down along the lines of stress. And what this means, right, for you and I is, one, it explains why we have these different projections, trochanters, all those terms you have to memorize in lab. But it also tells us that we need to use our bones if we don't want to lose our bones, right? And so having exercise, even if it's walking, right? Every step, that impact is actually sending signals through the bone saying, hey, this is getting used, we should make this stronger. So keep that in mind as well. So as we look at remodeling, this ends up happening, I'll go back. We'll come back to that. As we think about remodeling, what you want to realize is that something like 20% of your skeleton is actually replaced every year through this process. Again, it's setting you up on use and disuse of the bones. And so if you had a period of time where you were stuck on bed rest or you were laid up with an injury or something, right, you might actually see the bone getting thinner as osteoclast activity outweighs osteoblast activity. Remodeling is also super important in how we heal things like microfractures, right? So small damage to the bone that might need to be replaced constantly. We need maybe osteoclast to kind of clear out that damaged area, osteoblast to come back and build it even stronger. This is also, of course, what we do when we repair a big fracture, a break to the bone, and we can look at that here at the end of the chapter. Bone remodeling is also really important because it is how we release minerals to the blood supply. So that calcium and phosphate we talked about being stored in the bone, if we need some of that to be released, that is also through this osteoclast activity as part of remodeling. Okay, now there are a lot of nutrients and hormones that are going to play a role here. And again, thinking of bones as alive and actually this reservoir for nutrients can help make this make a little bit more sense. So let me just make a list here for us of some different nutrients that are going to be important in bone health. Okay, so probably the most obvious one is that we do need calcium in our diet in order to build strong bones. So calcium, sorry, I'll write that, calcium and phosphate are important in your diet for building strong bone. But you also need things like, do you recall we talked about scurvy in the tissue? So vitamin C is really important in how those osteoblasts lay down the collagen, that they can build collagen properly. Vitamin D comes up a lot, and we'll look at here in a minute how that's important in our ability to actually absorb calcium from our diet. There's a few others, but let's move on. Let's think a little bit about the hormones necessary for strong bones. So things like growth hormone is going to be important in telling those chondrocytes to continue to divide when we think about things like interstitial growth. Thyroid hormone tells our cells how kind of metabolically active to be. So both growth hormone and thyroid hormone kind of work together to stimulate bone growth. We'll see estrogen and testosterone. And their levels, particularly at puberty, are going to be what accelerates the ossification, how quickly that bone development is catching the cartilage division, right? And so at puberty, we'll actually see that epiphyseal line fuse, right? We've run out of cartilage, and now we call it, we call the epiphyseal plate. Once it's done growing, we then change its name to the epiphyseal line. It's fused. There's no more growth taking place there. And then a couple hormones that we'll spend quite a bit of time here going over are parathyroid hormone and calcitonin. Okay? Parathyroid hormone is going to act to increase blood calcium levels. Meaning it is going to take it from bone or tell us to absorb more or not pee it out, right? But it's going to increase blood calcium levels. Calcitonin is going to decrease blood calcium levels, right? And blood calcium level is one of those things that the body maintains in very tight homeostasis. The calcium in your blood is so important for nerve transmission, muscular contraction, blood clotting, and a variety of other things that take place in your body. And so we maintain this in a very narrow window. So let's look at those hormones in a little more depth here. So your book, I think, does a really nice job at kind of laying out how PTH and calcitonin work in opposite directions. Okay? So notice what happens here. They're saying if blood calcium levels are low, that is going to trigger the release of parathyroid hormone. And parathyroid hormone is going to talk to 3 organs in order to increase blood calcium levels, right? 1, it talks to the bones, right? It actually stimulates osteoclasts. And remember, our osteoclasts are those scrubbing bubbles, right, that can actually release calcium from the bone, right? That's going to increase blood calcium levels. Parathyroid hormone also is going to communicate, actually let's go here, to the kidney, right? And it tells the kidney, like, stop peeing the calcium out, right? It decreases calcium loss in the urine, which means we hold more of it in the body, right? We keep it in the blood. The other thing it triggers at the kidney is the release of calcitriol. Now, here's the, annoying thing, okay. Calcitriol is the active form of vitamin D. And we saw this in the integument, but we'll go over it again here in a second. But the kidney is actually releasing this vitamin D. The vitamin D is then going to work in relationship with parathyroid hormone to tell us to absorb more calcium in the small intestine and up our blood calcium again, right? So parathyroid hormone, with the help of vitamin D, right, is going to let us increase blood calcium, right? And that is PTH. Calcitonin, and this is where I get annoyed, calcitriol is vitamin D. Calcitonin is a hormone produced by the thyroid gland that is going to decrease blood calcium levels. But notice it's working on the same 3 places. So this is actually kind of nice, that what calcitonin does is basically tells the osteoclast to cut it out, right? We don't need more calcium in the blood, right? In fact, we want to bring it down. So osteoclasts stop. The kidney actually is told to go ahead and pee that calcium out. We have too much in the blood. And here's the funny thing, calcium is super important, but actually high levels of it can put you into cardiac arrhythmias, like weird heartbeats, weird muscular like spasms and things like that. So it is too much of a good thing. So calcitonin tells us to pee that out, and we then release less calcitriol, right? We're like, we don't need to absorb this, and so intestinal absorption of calcium decreases as well. And this is kind of interesting, right? So if you drink a glass of milk, but parathyroid hormone has been triggered, you will absorb more of that calcium. If you drink a glass of milk and calcitonin has been triggered, a lot of that calcium, that nutrient, will actually pass through your digestive system, not being absorbed. So kind of pretty neat how these feedback mechanisms work, okay? So parathyroid hormone and calcitonin, and do just make sure that you keep those two straight. Speaking of calcitriol, let's make sure we remember what was going on as far as production of calcitriol, right? We said this actually starts in the skin where UV radiation interacts with the cholesterol molecule in the skin, right? And it's going to create this molecule called cholecalciferol. This is figure 716 if you need to see that closer. Cholecalciferol goes to the liver where it's converted to calcidiol, and then that is going to go to the kidney where it's converted to calcitriol. Calcitriol is that metabolically active form of vitamin D that we were just saying is going to impact blood calcium levels. Right? So make sure you run through that one more time as well. If you find something that comes up in multiple chapters, that might indicate that it's going to be important. And I guarantee, yeah, okay. I guarantee this comes back quite a few times, even in AMP2, the difference between parathyroid hormone and calcitonin effects. Okay, last thing we want to touch on here, the end of the chapter really does kind of talk about what happens with bone pathology when things don't go right. Here they're talking about how fractures are repaired. They give you a variety of different ways that bones can fracture. This is actually 617, a really interesting panel. I won't go through and ask you the difference between a compression fracture and a spiral fracture, but pretty interesting. Now, the repair part, we should know, right? So when that bone is broken, keep in mind all that blood supply that we saw going through all the central canals, those sorts of things, there's a really rich blood supply. And so one of the first things that happens is you get this big blood clot forming at the site of a fracture. And this blood is actually really important, right? Because it's going to bring a lot of the nutrients and things that we need. So the second step of repair, we're going to get what's called a callus. So in that area that kind of filled with blood, we're actually going to see cartilage, right? We're almost going back to that kind of original template. Cartilage can form in there first, and then we're going to start remodeling it. We're going to turn that cartilage into spongy bone, and then we'll continue remodeling that back into compact bone. Now, notice that at some point during repair, this bone is actually going to be thicker at the site of the fracture than it was before. Remodeling is not completely done here, but this bone is already really strong. So even when a cast is removed, we're probably not completely done fixing that bone, but we've repaired it to the point where it is as strong. Okay, the last thing, I've kind of alluded to this a couple times. Keep in mind that due to those laws about use and disuse, that bone lays itself down along the lines of stress, that being physically active, particularly in your youth, and having adequate nutrients in your diet is going to allow you to develop strong, thick bones. But we also know that remodeling is this constant process, so you can't just be like, oh, I was an athlete when I was younger. You need to continue to use bone throughout your life, or it will start to disintegrate. Now, this happens anyway, right? So particularly around menopause, changes in some of those hormones are going to affect the way remodeling occurs, and typically osteoclast activity will start to outpace osteoblast activity, which is one of the reasons women tend to lose bone mass faster than men. But diet, exercise can go a long way into maintaining healthy bones.